Greetings to you. We are on the 17th lecture of this 20-hour program. Yes, last class I was teaching you about the determination of non-ionic surfactants, and as I was telling you that nowadays everywhere there are surfactants entering in our water analysis. Without going into too much of the detail, I would like to show you this slide, and next slide I had shown you the preparation of the reagents, and then this is the continuing the same vein. We prepare all other reagents, and this is the procedure. We had stopped somewhere here where I had indicated that the recommended sample volume is about 5 microliter, 5 ml, and cookbook value for 40 microgram of the surfactant you should get if everything is in order. In 10 ml, if you have this kind of surfactant standard value, it should give you an absorbance of about 0.32 plus or minus 0.01 at about 500 nanometers. So, this is the spectrum of non-ionic surfactant and Ki iodine system. You can see that the peak is somewhere around 400 here, but we are choosing somewhere around 500 I think for measurement, and this is the linearity curve, Beer-Lambert's law passing through the origin, and the linearity is wonderfully covered with R square value where you are getting 0.998. So, that means the curve is highly reliable. Now, we will move on to the interferences. In interferences, normally what we would like to look at, as I have told you, are the number of elements, and since I am not going to present it to you here, I would like you to record here the interferences of different elements, that is lithium, boron, magnesium, calcium, copper, cobalt, manganese. All these ions do not interfere. First I give you normally the non-interfering, and that also includes nickelus ion, zinc ion, chromic, that is chromium 3, aluminum, ferric, Fe3 plus, arsenous, chloride does not interfere, bromide, iodide, chlorate, etc. do not interfere, sulphate does not interfere, nitrite, etc. do not interfere, EDTA. In general, except any of the metal ions that we had tested in normal hello? Are you able to record me? If I show my...
No, the shirt you are wearing is this thing.
What?
Blue.
So?
Background, it glitters a lot.
Okay. What should I do?
We just can't put the PIP.
Huh?
We just can't put the PIP.
Okay.
It glitters a lot.
Can you put on the side?
No sir, it glitters.
Oh, I should have known that.
The thing is, the background is black.
Yes.
You are wearing it the same similar color.
Oh.
Only the face will be normal. This thing will be glittering a lot. It'll have some distinct lines and something.
So what to do?
You can continue without this thing, sir. The picture in picture.
Do you have a shawl or something?
No, sir.
It's there now.
That thing, no. It's the bigger one. It's full of dust.
Dust.
Junk.
Oh.
You can just continue like that.
You don't have a coat?
No, sir. We don't. Nothing.
Give me your sweater.
This one.
Huh? You wear only t-shirt.
No, I don't wear t-shirts.
Inside you don't have,
No.
only banyan. Okay. All right, we continue like this.
Yes, sir, sure.
Okay. Fine. That's why I got confused. Even when I am showing this.
No, I just tried doing it in that this thing.
Okay.
It was not appearing. It was glittering more.
Acha. So, now we continue our discussion on the determination of other parameters. That is, let's talk about iron. Iron in water can cause stains. In drinking water, it imparts a certain objectionable taste and turbidity. The Bureau of Indian Standards prescribes a limit of about 0.1 ppm. Where there is no suitable alternative source of drinking water, the maximum limit is 1 ppm. Okay. So, iron as such does not have any deleterious effect on the health of fauna, but in general it is not desirable. Whenever you wash clothes containing iron, it leaves stains, etc. So, the best method for iron is the determination of iron using 110 phenanthroline. This is a very old method, very well tried and tested method. And here we have to remember that it is the ferrous ion that reacts with 110 phenanthroline and not the ferric ion. So, ferric iron is usually in all drinking waters whenever you come across, because they are all exposed to oxygen and atmospheric dissolved oxygen and atmospheric oxygen, most of the iron salts are dissolved as ferric. So, it is important for us to first reduce the ferric iron to ferrous, and then we should react it with 110 phenanthroline. It is also known as orthophenanthroline, and at pH 4 it forms a red complex. The absorbance at 510 nanometer is related to the concentration of the iron. This is the structure of 110 phenanthroline, and the complex will form, the ferrous complex will form a bond with both these nitrogens, forming a complete ring structure. So, this is the one of the most celebrated organic reagent for the determination of iron, and it is a textbook for almost all standard textbook experiment at right from pre-university level to MSc level. So, the reagents we have, as I have already told you, that we have reduced everything to 100 ml maximum stock solutions, and I am giving you the details here. 0.7022 gram of ammonium ferrous ammonium sulphate crystals. You have to dissolve it in sulfuric acid. That means it has to be highly acidic. If the acidity comes down, most of the ferric and iron, ferrous as well as aluminum, they all precipitate, and we will not have any test result to show. And standard iron solution, we have to prepare about 100 ppm, and hydroxylamine hydrochloride we will need to reduce ferric to ferrous. So, that concentration I have given here, and then we will have to prepare sodium acetate acetic acid buffer of pH 4, 4.5. For that also you have to dissolve about 0.98 gram of anhydrous sodium sulphate in about 25 ml in dissolved deionized water, add 35 ml of concentrated HCl, dilute up to 50 ml. That is a very standard procedure, but here it is, you have a ready reference for using the preparing the sodium acetate acetic acid buffer. And then you have to dissolve 110 phenanthroline also in the same way, but you have to dissolve it in water. You can add a little bit of alcohol for easy dissolution. Of course, it requires a little bit of heating and stirring. So, because it is a very simple test, you have to add according to the reagents what I have given here, 10 ml, I take 2 ml buffer, 2 ml hydroxylamine hydrochloride, 2 ml of orthophenanthroline, and you have to dilute with to the mark with water, followed by addition of your sample. And then lambda max is at 510 nanometers. You have to pipette about 0 to 750 microliter of 100 ppm sample solution into 10 ml volumetric flask. This is for the standard. So, if you add all these reagents as I have indicated here, you will have a good curve, that is good measurement numbers, and the recommended sample volume is about 5 ml, and cookbook value for 100 microgram of iron in 10 ml, that is 10 ppm in 1 centimeter cell is approximately 0.73 plus or minus 0.01 nanometers, 0.01 absorbance only, sorry, not nanometer, but it is absorbance. So, this is the complex measured against its own blank. Usually blank is colorless in this case, and we have a lambda max around 510 or 520. 510 would be the most ideal one, and the calibration curve, as you can see from this curve, is very good, up to 150 micrograms in 10 ml, that is 1.5 ppm. So, it is a very sensitive method. There are other sensitive methods also using potassium thiocyanate, very good method directly for the determination of ferric, but there are a lot of interferences in the ferric thiocyanate method, whereas in ferrous orthophenanthroline there is not much interference, and we also note that the R square value for this, that is the linearity index for this is 0.993, not very good, because in good spectrophotometric procedures we expect between 0.997 to 998. 0.993 is not a very good one, but it has nothing to do with the method as such. It is a characteristic of the reagent or the complex, and the complex is stable indefinitely for almost up to 6 months. You do not have to worry about it. Now, I would like to give you some information about the interference of the other elements, and I have to tell you that magnesium, lead, fluoride, manganese, iron, iodine, aluminum, sulphate, nitrate, phosphate, tartrate, chloride, vanadium, molybdenum, borate, sodium lauryl sulphate, and triton X100 did not interfere. But then what sort of things will interfere in this method? Those include antimony, nickel, chromium, zinc, some of the transition metal ions, which also are capable of forming cyclic complexes with orthophenanthroline. And then EDTA interferes by forming a stronger complex which does not permit iron orthophenanthroline complex to be formed. So, you cannot use EDTA to mask the other elements in this case. So, then DTPA, that also interferes, that is another complexing agent. Cadmium interferes, cobalt interferes, etc. Some of these interferences can be overcome by reducing the concentration, but some of them can be overcome by using citrate citric acid buffer, that we are already using here to remove the possible interferences. So, I have a limit of nickel toleration, that is up to 100 microgram of nickel can be tolerated in the method, and cadmium also can be tolerated up to 50 micrograms, that is in presence of 1 ml of citric acid citrate buffer. So, I want to give you another method, that is the determination of phosphate. In the phosphate ion, phosphorus is one of the most abundant mineral in the earth's crust, and no national standard criteria have been established for concentration of phosphorus compounds in water. The reason is we use phosphate all over the world for agriculture as well as in some other industrial applications, and phosphate is used as a fertilizer, and it is a biologically essential element, but it has got its own problems in the environment, especially if nitrogen and phosphorus are there in the effluent or in a water body. There will be something known as the algae and other forms will plant forms will proliferate, and once the algae finish their lifetime, they all become dead mass, and this dead mass keeps on increasing, reducing the life of a water body. So, most of the water tanks in villages must be guarded against phosphate. So, to control eutrophication, phosphate should not exceed more than 0.05 milligram per liter, that is 5 ppm in a stream, at a point where it enters a lake or reservoir, and it should not exceed 0.1 milligram per liter, that is in streams, and these norms are normally followed very strictly with respect to the effluent, industrial effluent, especially from industries as well as municipal effluents. So, what are the typical reactions of phosphate? How do we go about determining the phosphate in a given sample? The best method is molybdophosphoric acid method. It is normally orthophosphate reacts with ammonium molybdate to form molybdophosphoric acid, and it is reduced to molybdenum blue by adding a reducing agent such as stannous chloride. The intensity of the blue colored complex is measured at 700 nanometer, which is directly proportional to the concentration of the phosphate present in the sample. A very simple method required in several applications and several laboratories, organic laboratories, inorganic laboratories, as well as in agricultural universities and factory effluent monitoring, very important. It is also used as a special component in most of our washing machines, washing powders, detergents, washing powders, etc. There is a lot of phosphate usage, and that makes it a bit tricky, especially because the most of the washed phosphate ends up in the river water systems. So, these are the reagents. What all we need is a phosphate solution, standard phosphate solution 10 ppm. You can prepare 100 ppm and 10 ppm standard stock solutions, and then all the solutions are soluble in water. So, then you have to prepare ammonium molybdate reagent that is available across the shelf, and you have to dissolve it in deionized water, add about 28 ml of concentrated sulfuric acid, and then cool and dilute to 100 ml. Stannous chloride is another important reagent which is a reducing agent. So, you have to dissolve stannous chloride with in concentrated HCl, and slowly you have to stir and boil, etc. This is a little tricky part. If you do not have very good stannous chloride, you will end up with a little bit of difficulty. Therefore, I suggest you practice it quite a 2-3 times on smaller volumes and see whether you get clear solutions. If the pH is not correct, then you will end up with a heap of precipitate which will go waste, especially of stannous hydroxide. And then we need EDTA for the complexation of the typical elements present in water, and that you prepare by dissolving 3.72 gram in deionized water and make up to 100 ml. So, the procedure involves 0 to 10 ppm of standard phosphate solution, followed by addition of 1 ml of 0.1 molar EDTA, that is a complexing agent we add first only along with the sample, and then we add about 0.2 ml of ammonium molybdate reagent, followed by 20 microliter of stannous chloride reagent to each. So, dilute to 10 ml with deionized water, and after about 5 to 10 minutes you can measure the absorbance at 700 nanometer against a typical blank. So, this should be followed by calibration curve, and it can be a recommended sample volume is about 5 ml, and the cookbook value for you for phosphate is 0.5 microgram phosphate solution should give an absorbance of about 0.39 plus or minus 0.02 in 10 ml of the final solution. So, this is the spectrum of phosphomolybdate blue, and you can see that the lambda max is somewhere around 700. It is fairly flat in the maxima region. So, you can use even a colorimeter for the determination instead of a spectrophotometer. Okay. And this is how the calibration curve looks, and we have a fantastic correlation, that is linearity is 0.999, and this is one of the best method as far as my experience goes for the determination of phosphorus, because the concentration is always within this range, especially in storm water and river water, pond water, etc. So many times my students have completed this analysis very regularly, and we have always ended up with the recommended absorbance range, that is 0.39, and now I would like to show you some of the interferences that are expected. So, you may note that nickel does not interfere, and usually 100-fold range cobalt, nickel, copper. Copper does not give any color, there is certain definitely some amount of interference, and zinc gives interference, molybdenum, all these things interfere. Many of the metals, for example calcium, magnesium, etc., in about 100-fold excess they do give white and black precipitate. For example, lead gives a black precipitate, bismuth gives a white precipitate, etc. And among the anions not much interference is expected, because chloride, bromide, iodide and fluoride, sulphate, nitrate, EDTA, SLS, etc., they do not interfere. But of course, SLS interferes, and for those things we have tried almost all complexing agents, and what we find is 10-fold excess gives you certain amount of interference, but still it is not very good. So, but equal amounts, there are no interferences from aluminum, magnesium, molybdenum, etc., antimony, but antimony, bismuth, etc., they do precipitate, so they give interference, but they precipitate as hydroxides, not as a complex. So, tenfold fluoride etc. in tenfold excess does not interfere. And then we have tried couple of complexing agents, for example glycine as 1 ml of 0.1 molar glycine we have tried, and in glycine also we found that most of the cobalt, copper etc. they do become turbid, but equal amount of phosphate does not give any interference. For example, if the concentration of phosphate is around 30 to up to 2 ppm, 2 or 3 ppm, the interference will not be there. So, copper, cobalt, zinc, cadmium etc. they do not interfere, especially if the interference is very less, because these elements are not there in presence of in the almost the same quantities you will not usually come across. So, same thing, but to our dismay we found that the phosphate there is certain amount of interference which we could not remove, that is arsenic. Even 0.5 ppm arsenic keeps on interfering, and 100 ppm level, yes, we could manage it to some extent. So, with this interference data I would like to conclude about the stannous chloride, and then the next element on my radar is nitrite. Nitrite is one of the important interfering element present in water, not desirable because it reacts with primary aromatic amines, and then nitrites are implicated in the blood reaction with hemoglobins, and they do give certain carcinogenic complexes, give rise to generation of certain carcinogenic substances. Therefore, nitrite has become an important pollutant to be determined very regularly with drinking water. So, with this introduction I would like to say that in acid solution nitrites do react with primary aromatic amines to form disonium salts, very standard organic chemistry reaction, and the latter give intensely colored azo dye stuff with aromatic compounds containing an amino and hydroxyl groups. So, these dyes are suitable for photometry and the reaction is specific and very sensitive. We will continue our discussion after about in the next class. Thank you.